And I'm going to share my screen. And I think I kind of, it's a little ironic that I chose this article because it's about anxiety about statistics. So I kind of like the irony of it. One of my friends actually did this research. She was looking at the relationship between graduate students, statistics self-efficacy, statistics anxiety, attitude towards statistics, and social support. So when we talk about self-efficacy, we're talking about a person's belief that they can do something. It doesn't mean that they can actually do it. All right. It's just the belief that they can do it. So it's, basically having confidence that I have what I need and I can accomplish this. So what I want to do is, because I've gone through the parts of this in a previous tutorial, I hope some of you have taken advantage of that, where I talk about this article and talk about all the components of it. But what I really want to focus on are the results, which I find that most graduate students like to skip the results section of articles and skip on down to the discussion. But tonight we're actually going to look at the results and break them down. All right, so let's go down here to where we get our, here we go. Okay, so this part of the results, this table 1, from self-efficacy, that column, statistics anxiety, attitudes towards stats, social support, that section of this table is called a correlation matrix, right? And it's very common. This is a very common type of research that we see done in research, in social science. And correlation is simply looking at the relationship that variables have. There's no causation. So I cannot say something caused the other thing. All I can say is, as one goes up, one goes down. As one goes down, one goes up. As one goes up, they both go up. Or as one goes down, they all go down, right? And I can't even say which way the direction of that is, really. And so there's some things that when you see these correlation coefficients, which is what this is called, this number right here is called a correlation coefficient. It's also represented in statistics as an R, small r. And so you've probably seen R equals whatever, right? And R is the relationship between those two variables. So when I look at self-efficacy and relationship to self-efficacy, not surprisingly, it's 1, because that's the largest correlation you can have. That's the strongest correlation you can have, is 1. You can only be 100% related to something. So when you talk about, I have a brother, my brother and I have a mom and a dad that are the same, we are 100% related, right? 100% related. Whereas my ex-husband, he had a sister who was a half sister. They shared a mom but had different dads. So they were 50% related. So it was a less strong relationship. Still related, but not as related, right? So that's the span of it. Correlations can run the gamut from -1 to +1. One of the things that gets a little confusing for students is they think that negative has something to do with the strength or the positive, and that is absolutely not true. So when you think about the strength of a relationship, it is totally based on number. Forget the symbol, okay? Literally forget about the symbol for a second. So you take away the positive or the negative. It doesn't matter if it's positive or negative. If it's over 50 or over 60, it's going to be a pretty strong relationship. Even if it's a negative 0.67, that's a strong relationship. That's a good relationship. There's something going on there. There's something happening in that relationship. So that's good. So that's the first piece of information we can get from our correlation coefficient. The second piece of information that we can get, so first is the strength. The second is the direction of the relationship. And that's where the symbol comes in, the negative and the positive. That's what that's telling us, is in what direction is this relationship going? Is it positive, that as one goes up, the other one goes up? Is it negative, that one goes up and one goes down? What's going on here, right? So you get the strength and you get the relationship. The next thing that we can do with our coefficient, our R, is we can use an effect size. And the effect size for correlation is called an R square. So sometimes you'll see R square. And R square, when you square this number, this 0.679, when I square that, that will tell me how much variance is accounted for by the relationship. Okay, so how much variance how much variance is in self-efficacy as somebody's anxiety goes up or down. Okay, how much variance, how much change, but it's not cause. I have to really stress that. It's not causation, it's relationship. It's just saying that, you know, if there's a lot of cars out there, I might not get to work on time. Like, because there's going to be a relationship in the amount of time it takes me to get to work, right? But that may not be the only cause. All right, and then the other thing is that, so we have the strength of the relationship, which is the number, the direction, which is the symbol. Then we have effect size, which is the variance, and that tells us if it's meaningful or not. And the other thing that we can determine is we can also determine if we need to keep all the variables. When we're looking at a correlation matrix, one of the things that I want to do is see if all of the variables are distinct from one another. They're in the lectures, I think they talk about overlap, right? And some of you might have heard that overlap term. Well, one of the things that is actually more correct to say is, I'm trying to figure out how to get my Zoom to come up so I can put this in the chat for you, but it's not giving it to me. There it is. Okay, is multicollinearity. And so I want you guys to know the right word. So I'm going to put it in the chat. Multicollinearity. You get really excited when you learn how to spell that. Multicollinearity. So multicollinearity is the overlap, the amount of overlap that exists between two variables, okay? So let's pretend like this is variable 1, post-it number 1, and this is variable number 2, all right? And I'm trying to see how much they explain my to-do list, something like that, okay? And so what'll happen is, if I want to predict something in using correlation, I would add up the variance that each one of these accounts for, and I would be able to say, okay, this is going to predict X. So a great example that we use a lot is high school GPA and maybe your GRE scores for predicting success in, well, let's say undergrad. Undergrad GPA and your GRE should predict, not really, but should predict your graduate school success, right? So you have your GPA, and you have your GRE. The problem is that these two variables are so related that they kind of look like this, right? They overlap, right? They don't explain distinct variance in graduate success, right? It's the combination of the two that explains the graduate success. I can't separate them out and add them together and get an accurate equation because there's overlap. Because if you got a high GPA, chances are you're going to probably do well on the GRE, right? So there's some overlap here, multicollinearity. There's overlap. And that multicollinearity is problematic because I can't just pull that piece out and say, okay, I'm going to add this, then I'm going to add the multicollinearity piece, and then I'm going to add this so I can figure out my prediction equation. It's not that easy, and you can't really say like exactly what the overlap is and how to pull that apart. So when something has a lot of overlap, as a researcher, I have to decide, am I going to keep both variables in here and predict the relationship? Or am I going to choose which one of these I think is a better variable and get rid of the other one? Okay, and it's subjective. It really is a very subjective process that we decide what we're going to keep and not. So when I'm looking at this correlation chart that we have in this particular study, what I notice is attitudes towards statistics and statistics anxiety, which are two separate variables measured by two separate instruments, they have a really high, strong correlation, right? It's a negative correlation, but it's still a strong correlation. So in this, the lower the attitude about statistics, the higher the anxiety. So it's a negative relationship, right? The other is true too. The better my attitude is about statistics, the lower my anxiety is. But they're so related. As a researcher, I can't pull it apart because 83, right? Well, it's not really 83, it's more, let's see, 0.832 times 0.832 equals 69%, because I square it to get the R square, right, to figure out the variance. So when I square that coefficient, it gives me 0.69, which is telling me that 69% of the variance in attitude up, test anxiety, or anxiety up, attitude down, and vice versa, 69% of whatever change happens is accounted for by that relationship. Right? So what that tells me is if I'm trying to predict self-efficacy, which is my dependent variable, if I put both of these things in the equation, I'm going to over predict because this part that's on both of them is going to be added in there twice. Because when I add this variable, I'm going to be adding that section. And when I add this variable, I'm going to be adding that section, right? But it's not really like that. It's an overlap. So that overlap has to be accounted for. Okay, or I have to throw one out. And that's when I have to make decisions. And so in this case, how would I make that decision? Well, when I look at attitude towards statistics in relation to self-efficacy, it's 0.70. I don't care about the direction at this point. That's not how I'm looking at the strength of the relationship. Statistics anxiety has a relationship of coefficient of 6.67. Now, it's rarely this close. Usually it's pretty much more clear, but in this one, if I'm just mathematically making that decision and I was going to throw out a variable, I would throw out statistics anxiety because it has a weaker relationship with the dependent variable than the other independent variable. Does that make sense to everybody when you're reading this? Okay, because this number is lower than this number, just the numbers, so to speak, then I would, if I was making a decision to throw something out, I would throw this one out. But that's really close. That is so close. Okay. The other thing that we have to know is, are these variables that we're looking at, are they significant? Okay. So mathematically, did I have enough data to really know that the variables were the relationship, and it wasn't just because of chance that I got this correlation coefficient, right? Because when you're doing statistics, you really have to have a large number of things, a large number of data to be able to see relationships, right? If I only have, you know, scores for you guys, right? There's 7 of you. If I have scores for you guys, I'm not going to be able to see themes and patterns in the numbers as much as if I had, say, 300 scores from different graduate students. So the more I have, the stronger I can make inferences from my data, okay? And what the p-value, this last column, is saying is whether or not this is a mathematically significant finding. If it is not a mathematically significant finding, it doesn't matter what the number is, okay? So if I don't have something that's less than 0.05 in the p-value, you don't even look at it. Like it means nothing. It's trash. It doesn't mean anything. So if your result is not significant, do not even include it in your assignment, okay? Because it doesn't mean anything if it's not significant. And in social science, we tend to accept a p-value of 0.05, which means that I want to be 95% sure that my results are really because of what I was studying and not just because of chance. I'm willing to be wrong 5% of the time, but I want to be right 95% of the time. So I have to have a number that is less than 0.05, because that's saying, in this first one, it's saying that there is a 0.3% chance that I'm wrong. I'm okay with that. That's okay. I can take that risk, right? This one's saying 0.1%. But what is this one saying? This one's saying that I have a 59.3% chance that I'm wrong. Are we willing to accept that level? No, this is trash. So I'm gonna throw social support out just based off that alone. The data doesn't mean anything, okay? Because it's not significant. It's not a significant finding. I probably didn't have enough data to find that theme, okay? So that would not even be included in my, like, I would say it wasn't significant. So I'm not gonna talk about it because the data doesn't mean anything, right? So if your p-value is greater than 0.05, out. Now, a lot of times what they'll do, a very common way to report that in research, is that what they will do is they will put, in this case, they would have put a 1 asterisk beside this number. They would have put a little asterisk right there, single asterisk. And that single asterisk would signify this result is significant at the 0.05 level, all right? But for this one, they would have actually said this result is significant with 2 asterisks because it's significant at the 0.01 level. That's pretty significant. I'm 99% sure that I'm correct, okay? Actually, in this case, I'm 99.9% sure. So 1 asterisk means it's significant at the 0.05 level. A 2 asterisk means that it's significant at the 0.01 level. Now, do we say, oh, this one's more significant than the other? Nope. In stats, it is significant or isn't significant, but we just let the people know how sure we are. Okay, so I've broken down this chart. What questions do you have? And please know that if you have a question, or you are confused, at least 2 or 3 other people probably are.
Okay, so on one question I have is just based on this and in the assignment. So we also see these other numbers here, and we see the mean numbers and deviation. Are we just supposed to ignore those numbers?
Yep, don't worry about that. Mean is just your average, right? So it's just saying of the data set that I had, this was the average mean for self-efficacy, which is important when you describe it, but for the purpose of the assignment you're doing this week, doesn't mean anything. Okay, it's not related to the correlation. The mean and the standard deviation are your descriptive statistics that describe the data set so that you can say, this is what my data set looked like. All right, you might also have range in there. You might have a minimum score and a maximum score. You know, those are also really good ways to check your data, right? So if I'm using a self-efficacy instrument and the instrument reports that on average, when you look at the general American population, on average on this instrument, we anticipate for graduate students, the mean score is going to be plus or minus 1 standard deviation, a 40, okay? Let's just say that the instrument information that you have says that, right? Plus or minus 40. Let me explain what that means. So in this case, we got a 49, right? But we're saying the average score for the rest of the people who've ever taken this test was a 40. When I do 40 plus 18.97, which is the standard deviation, that gives me 58.97, right? So that's the plus 1 standard deviation. So what I can say, the way I would interpret that, right, is in this case, I would say that the data collected for this particular research study was within 1 standard deviation of the national norm, with a mean average of 49.73 and a standard deviation of 18.97.
Yeah.
Okay, but that's not part of this assignment, but I wanted to just tell you how you would read that.
Okay.
Okay. All right, and then the beta and the standard error, those are important for calculating other things, but you don't need them for this particular assignment. And I would invite you to take my inferential statistics class at the doctoral level when you're ready, and I'll explain all this. Okay?
Okay. Got it.
All right, so other questions?
In the lectures, so generally we're looking at, in terms of these, the relationship being strong, moderate, mild, or whatever, that he uses 3 categories.
And you'll see it different ways. It's small, medium, large, weak, medium, large. I mean, you'll see it written out different ways.
Okay. But we should more or less go with his 3 categories, right?
I really don't care. You can do it. I'll know what you mean. If you say it's a strong one, I'll know what it is. If you say it's a large one, I'll know what it is.
Okay. Yeah. Some of the videos divided up differently in terms of, where those starting points and stopping points are.
Yeah.
Yeah. And then he does a predictive study
Mhm.
in the end, and he's really looking at the, if I understand it right, the R square value
Um,
in that predictive study, and doing some similar analysis. It seems like he's using the same framework of scores, but I guess I was
yeah,
getting a little confused because he was looking at R square there, whereas in the other ones, like here, he's looking more at the R value.
right.
Am I understanding?
So with this particular correlation matrix, this is a Pearson correlation coefficient because all of your data is scaled. So it's an interval numbers. Okay,
Right,
so this
right,
is Pearson. When you move into predictive equation, most commonly you guys will see multiple regression or
right.
linear
That's what he's doing there.
regression.
Yeah.
Right. With that, that's where you're going to be using your betas and stuff. You're going to take the coefficient and you're going to multiply it. You're going to do all the data. So let's pretend like this became a predictive equation, okay? So I'm trying to predict self-efficacy we're just going to use stats, anxiety, and attitude towards stats. We're going to keep them both, even though I know they're multicollinearity and I probably throw them out. Anyway, I take that coefficient that it gives me, okay, and I put that into a formula. So literally, I would do something, if this was the coefficient, it wouldn't be this, but I'm going to say 0.67, a negative 0.67 times x plus 0.708 times x2 plus, and then that's going to be my constant. It's called a constant. You'll get this thing called a constant. A constant is where, when you think about a graph, right, you have an x-axis and a y-axis. If I were to plot this line of best fit, if I were to plot all the data on there and draw a line through the data that was the best middle ground line for all of those, where does it cross the y-axis?
Right.
Okay, so it looks something like this. So I know my handwriting is not good. So it'd have the coefficient times x, which is my first variable, plus the coefficient of the second variable, x2, plus the constant, which is the y, where it crosses the y-axis.
Okay.
That x, in this case, would be, let's say Sarah. Sarah's coming after I've done all the research. I've come up with this equation. Sarah's going to be coming into my stats class. And I'm like, Sarah, I want you to take these instruments. I want you to take a measure of your stats anxiety, and I want a measure of your attitude towards stats. Those same instruments this study used. She takes them. She gives me her scores. I can plug her scores for those instruments into X and X2, and I can predict what her self-efficacy is. Why is that important? Because as a counselor educator, if I can predict somebody's self-efficacy, then I know who might need additional support in the class before
Right.
they even have trouble in the class.
Okay.
Does that help, David?
Yeah, I think so. I was just curious. I noticed that. Yeah, is he?
And I know he's using some different terms, and we're going to try to clean that up, by the way. But it is important to kind of, I want you to be able to read an article like this and be able to go, well, why did they keep both anxiety and attitude? That's a really high relationship there. They shouldn't have kept both of those.
Right.
Right? They're
Right.
over predicting. That's what I want you to be able to do. I want you to be able to become a critical consumer of the research. This would not be highlighted in yellow usually. I highlighted in yellow because I wanted you guys to see it. But I want you to be able to look at this correlation coefficient and go, okay, are all of these independent variables distinct? Because in a really solid, good prediction or relationship, I would want the independent variables, statistics, anxiety, attitudes towards support, and social support, to have very low relationships, very small relationships with each other, like a 0.006. That's a great one, or social support in relation to social anxiety, right? Or statistics anxiety. That's the type of correlation I want my independent variables to have, because there's not much multicollinearity, right? It's barely overlapping. Okay. But then I also know social support wasn't significant and it got thrown out. So that tells me that's another factor into my decision. So I might say, well, you know what? well, that's pretty low. So maybe I should keep stats anxiety instead of attitudes towards stats. So you have to kind of play out all the different components to figure it out. But when I read this article, which I've actually asked Michelle, like, why would you keep that? Like, why would you keep that when you know there's that much overlap, right? And it would be irresponsible of researchers not to talk about it. She does, but it would be irresponsible to not talk about that, right? Why you kept it, how you made that decision. You need to explain all that and so as a researcher or as a practitioner, you need to look for that. Like, you want the explanations for why they threw out one and kept the other, or what, they did with that, so that you can know, is this study really solid enough for me to be using it to inform what I'm doing with my clients? Sarah, you look like you've got deep, deep thoughts. So I'd love to, what you thinking? Tell me, share. She's like, I don't even know what to say yet.
I don't know how deep they were.
Okay.
I was just thinking about the different, like the chart for the assignment, and then the ones that we've seen from, I think, possibly some of the other assignments. Mm-hmm. And so I was just trying to remember what I had, if I had interpreted all of that correctly previously. So yeah. Probably not, actually.
Well,
so.
You have to remember, I've been doing this for 20 years. So when I just like, blah, 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 it's like, I teach stats. I love stats. It's one of my favorite, it is my favorite course to teach, actually. And I mean, it's what I'm very passionate about. So this is something that to me is like a puzzle, and I like to solve the puzzle, because I love jigsaw puzzles. And when you try to put a jigsaw piece and it looks like it fits, but it doesn't really quite fit, and you get to the end and you're like, why won't this come together? This little yellow guy here is that piece that almost fit in another spot, but didn't really fit to me. That is like glaringly, a problem. Andrea, what about you?
I mean, what is the goal of this study again? Like, was it related to, I don't see the title anymore. Like, is it
self-efficacy
related to, because I was under the impression that there are a lot of cases where you'd be like really excited about having a strong correlational relationship, and that the stronger the relationship, the more excited you are. And I guess is it in this case, is it that they're trying to validate a survey or something like that?
No, let me show you, because that's a great question. Okay. You see this line I just put in blue?
Yeah.
Okay. So self-efficacy is my dependent variable. So that's the variable that I'm trying to measure as an outcome. I want to know what the variance is in that in relation to these other variables. Okay, so I have three independent variables. I have, or what we would call predictor variables.
Oh, right? Self-efficacy is the only dependent variable.
Yeah. So I'm using these.
So they're saying like so it's basically saying we don't want it to be too high. Otherwise, we might be measuring self-efficacy. We don't know.
Well, no, what you're doing is you're measuring, let me show you.
We don't know if what we're looking at is the same, right? Yeah. Like, because the measures might be not teasing apart the two variables, so you don't want it.
Right.
I guess in one case, like, where do they want to see it at? Like, at a 0.5, like a 5? No, I'm not talking about
it's very subjective. Okay, so when I draw this as a Venn diagram, this is what it looks like. So these are my independent variables, right? So this is, and I just did the first three. So this is statistics anxiety, the first circle, and it's overlapping with attitude towards stats. See that 0.83? So that's this area right here. Okay. And then this one, when you do social support and attitudes towards that, they're overlapping by 0.017, that tiny little bit, right? But what happens is mathematically, it really, when I do it as a mathematical problem and trying to determine what the variance is going to be, mathematically, it's going to try to force it to do this. Okay, so it's going to try to add each one of these independent variables independent of each other, but they're not independent. So what happens is this section and this section, the two sections that I've shaded, are being added in twice because it's being added when I use this one and it's being added when I do this one. And for this, it's adding in here and here. So those shaded parts are getting added in multiple times. That's the overlap. That's the multicollinearity.
Because basically another way to think about it is that obviously you have these two measures, they will probably self-report like some type of maybe validated survey. So the same, I don't know, I'm just trying to, like, my brain tries to
So you have two
understand it in different ways, but like the self-efficacy, I'm imagining a survey. Self-efficacy is measured using a certain survey or set of items. Maybe there's one full survey that measures self-efficacy, or maybe there's some big survey and there's a handful of items that are supposed to be measuring self-efficacy. And the same thing with statistics, anxiety, or attitude.
Yeah, there are. There's three.
So those things are
instruments. Yes.
So those things are being asked to people completely separately, and then
but they're covering the same constructs.
Okay.
Do you understand? So when I think about test anxiety, I mean, can we really pull apart what's only testing or statistics anxiety from attitude towards stats? They're so interrelated. How would we pull it apart? And we know they're really interrelated by this 0.83. That's a really strong relationship, right? That, you know, as my attitude about stats goes up, my anxiety goes down.
So, but when I say it seems like they're almost the same thing, you said no, though. Like, that's not the way to think about it.
Right. That's what the correct. I would say it's about the relationship. Like, it's really impossible to pull them apart. Okay. Think about multicollinearity. Here's another way to think about it as conjoined twins. Okay. We have conjoined twins. How do we pull them apart safely? Right. It's going to be very difficult to do that. That's a very complicated process and sometimes impossible. Right? And these two are very conjoined. They share so much in common. It's really hard to pull them apart to say what impact does this one alone have and what impact does this one alone have.
Okay. And they just have to decide where that cutoff is. It's just exactly. Like some random number.
No, I mean, my first decision would be, was it even significant? Because if it wasn't a significant finding, that would be easy, right? I would throw one of them out, the one that wasn't significant. If I had this high a correlation, say, between attitude towards stats and social support, then it would have been an easy decision because social support wasn't significant mathematically. Yeah. So I could have thrown that one out and kept the attitude towards stats and not worried about it. Does that help?
Yeah. Thanks.
Mm-hmm. David, you asked some really good questions about the assignment. Have I answered or given you enough information to help, or do you want to ask some more? Because I don't want to leave you hanging. Oh, you're on mute. Sorry.
I'm on mute. Okay. Yeah. No, I guess I still have some of those questions. The way I'm reading the assignment that we have, I don't see us getting into a lot of multicollinearity. I can't say it. I'm sorry.
Multicollinearity. I know it's
multicollinearity.
It's like etymological when you finally get to learn how to say it.
There you go. But I don't see a lot of that in the assignment itself. I think my one specific question was in question number 3. It says, is there evidence that these correlations are different from 0? What is that evidence? And I think from the lectures, I have an understanding of what he's trying to get at. But what is the antecedent of these correlations? In questions number 1 and 2, he says in 1, what are the largest reported positive and negative? And then question number 2, how would you describe both of these correlations? Is there evidence that these correlations are different from 0? So all 3 of those questions referring to the exact same 2 numbers Am I reading that correctly?
Yes, I would say yes.
The biggest positive or negative ones that we select.
Right. So
I mean, does anybody really have anything to say? Except, I guess, is there evidence that they're different from 0? I mean, is that a statistical, like, is that a statistical question?
Yes,
Just, like, I know that they're not 0 because I see, I mean, honestly, like, I see the number right here and, like, it's not, I don't know how to, like, am I just missing something?
Like in number 4, right, where you have E, F, E, R, okay? And you have negative 0.04. Okay, in that one, I would say, I don't know that one's different than 0. Why?
Because it's so close, I guess.
There's something else missing.
Because it's not significant, right? Due to if something's not significant, we don't know that it's not 0.
Exactly.
We can, it's, I think, I'm glad.
Okay.
Are the ones that are not significant the ones with the dashes through them?
So the dashes, this is really cool. So the dashes, because it's 1, because IFER is the first variable. So when you come across and you go up, that's variable 1 correlated with variable 1. Like self-efficacy was correlated with self-efficacy on my example. In that chart, it had a 1. Let me go back to that so you can see that. So here, see how they had self-efficacy was correlated with self-efficacy? And then statistics anxiety, when I come over under statistics anxiety, it's correlated with 1. And we would hope that the variable would be correlated 100% with itself. If it's not, you've got you have a data entry problem, right? Okay. If I come up with a correlation and the variable is not 100% correlated with itself, it's a problem. The other thing you'll notice is that on correlation matrix, half the data is missing, right? This bottom half. And the reason being that when you have your 1 diagonal, everything on the other side of it is just a mirror image of what was above it. Okay? So this number would go, let's see, attitudes to self-efficacy would go right here. It would be the same exact number. Because it's the same relationship, right? This is self-efficacy to attitude. Well, self-efficacy to attitude is going to be the same number. So we don't need to report it twice. I just saw a light bulb.
Okay.
With Emily. It was awesome.
So the dashes are ones that have already been
reported. Yep.
And listed.
Yeah.
Essentially.
Yeah, so in this one, they're all, the ones that are dashes are 1s because they're correlated with themselves.
Right. It may seem sort of obvious, but your vertical columns are exactly the same as the horizontals.
Exactly. Yes.
Does that make any sense? You may be looking for what does 1, 2, 3, 4, and 5, 6 mean. It means the exact same as.
Right. So this could say IFR. This would say EDR. This would say IDR. This would say EFDR. This would be depressive symptoms, and this would be psychosomatic symptoms. So it's the exact same list, horizontal.
That took me a while.
Okay. And see, here's where they explain the asterisks. Here.
Could you explain number 3 again for the assignment? Because I had a little bit of trouble understanding the 0 and that concept.
That's not the only way to answer that question, okay? But in this particular one, I'm just going to use the exact same one that I used, which I think was this one, right? Yeah. The reason that I know that I don't know that that's 0 or not is because it's not significant. So that result could be just by chance alone.
Okay.
So
if it's not significant, like if you have one that's significant, you can look at it in relationship to 0.
Right.
Okay.
Yep. And then you would be able to answer, well, this one's really close. It's not 0, but it's really close to 0, but only for the ones that are significant.
Okay. That's a lot easier then.
Okay. Good.
For me to understand.
Yeah.
I think I have a question.
Yes.
So does that mean that, and to make sure I'm clarifying this right, that's all like, I mean, I know it's connected, but to like p, the p value or whatever, where it's greater or less than 0.05 or 0.01, that's what means something significant.
Right. And it's not that one is more significant than the other. They're both significant, but this is the level. Like one, I'm 95% sure I was right, and one, I'm 99% sure I was right.
So when you go to answer question 5, where it asks if we agree with the conclusion that the correlation does demonstrate considerable correlation, you're basing that off of, because most of the coefficients.
You're basing that off the 4 areas.
Okay.
Strength, which is also here said magnitude, which is the same thing. Remember, that's the number, right? And it doesn't matter if it's negative or positive. The number alone determines magnitude.
Got it.
It's really important to understand that with correlation. The second one is the direction of the relationship, which is determined by the sign, the symbol, positive or negative. Then you have your significance, right? And then you have your variance, which is your R square when you square your correlation.
Okay. Got it.
So all of those would determine. Okay, so if there's one in here that I think does demonstrate considerable correlation, then I would square that number to see how much variance is accounted for.
Okay.
So the 4 steps, and I explained that in my announcement yesterday too. I have those 4 steps laid out for you in that announcement. Wendy asked a really good question. I wrote that response to her.
Okay. That makes more sense, because I think originally I was just looking at like numbers, like altitude, and so that helps a lot.
Yeah. So you got to remember the 4 components.
Okay.
I have a question.
There, yes.
Why are there 2 different levels? Why are there 2 different p values?
Oh, and that one is again. So in social, I'm trying to figure out how to answer it, Sarah. So in social science, we almost always set our p-value at 0.05. All right, saying that we are okay with we're okay with our findings being by chance 5% of the time. Okay, you know, this is where you're going to type 1 error, type 2 errors, things like that. You've seen those talked about before, I'm pretty sure. Okay, so in this case, what's happened is when I put my data into the computer program that found the results, it is able to determine the exact significance level that this data is accurate for. All right, so when we test our hypothesis, we're saying we are wanting to be right at least 0.05. But when we get our results out, say from SPSS, the statistical package for social science, because it's this amazing mathematical computer program, it can actually tell me the exact alpha level that my data is accurate to. Okay? So when I get those results, then if I have one that's at is less than 0.05 but greater than 0.01, I report it as less than 0.05. But if I have one that's less than 0.01, then hey, that's cool. I'm 99% sure this is not by chance alone, and so I would want to report that level of, power.
Okay.
Does that help?
Yeah.
Okay.
I heard you say something like at the 0.01 significance level, you wouldn't say that it's
better.
Why?
I know. Just because you can't mathematically be more significant. I know that's true. You are more, it's not more significant, but you are more confident in your findings.
Oh, right.
A better way of saying it. Okay.
Did I hear you correctly in saying the last of the 4 steps that we need to cover? It's sort of, you wouldn't necessarily go to the R square value without first determining if it was.
Yeah.
It has to meet the other 3, so it has to be something significant. There has to be strength, direction, and significant. So you whichever ones meet that criteria, you want to take it to the 4th level.
Right.
Correct?
Then you would be able to say that it accounts for this much variance between in the relationship. Yep. Exactly, David.
So when you're looking at like the direction, are you looking at the group of numbers as a whole?
Tell me more, Jessica.
So like when you're going, let's say you're looking for if one of the coefficients has, you want to look at the variance. So when you're looking at variance, you're only looking at one, right? So like say we took like 0.58, right? We'd only be looking at the variance of that.
Yeah. So yeah, because you have to take the R and you square it, right?
Yeah.
So like if I'm looking at, let's pretend the one I have highlighted was significant. We're just going to pretend like it is, okay? And so we know it's not. And so we have 0.04 and I multiply 0.04, right? And it tells me that there's a, I don't even know how to say that. It would be a 0.16% variance.
Okay.
Okay, because I squared it, right? The 4, I squared it. So that means that between EFR and the third variable, which is IDR, that if that were significant, it would explain 0.16% of the variance would be accounted for by that relationship.
So do you want a high variance or do you not want a high variance?
Yes, because variance is saying that as one changes, there's going to be this percentage of change or of variance in the relationship.
So you're looking for a higher variance,
right? Not causation.
Yeah, no, variance.
Well, but in that instance, you're looking at 2 of the independent variables. So are you wanting high?
I was just using that as.
Oh, okay. Okay. So
yeah.
But if I understand it right, from the first, what you were saying before, you're actually looking for this may be oversimplification.
Dependent, yes.
Yeah, in the dependent variables, you're looking for a high variance, but in the independent variables, you're really hoping for low variance because then you might be having a lot of overlap, correct?
Exactly. Yeah, you're right. You're right. So I'm looking for a strong relationship, which would equal high variance between an independent variable to the dependent variable. But when I'm looking at the independent variables against each other, I want a low relationship because I want them to be distinct. Got it? I'll say it again if I have to. So. Remember my picture, Jessica. These variables are explaining this variable. I need these to be distinct, right? I need them to be independent of each other. But I want them to be related to this because I want them to help me understand this.
Yeah.
I see the big question mark on your forehead.
Yeah. Me and statistics struggle a little bit.
So you're recording this video. Is this going to be like also posted later for us to go back and watch it when we do our homework?
Exactly. As soon as it renders, I'm going to post it for everybody.
Oh, perfect.
Awesome. And just question number 5, the way it's worded, would you agree the author's conclusion that these correlations demonstrate considerable correlation?
Which is what gets to our discussion, right? And so part of our discussion is how you interpret a correlation.
Okay.
Okay? Because
I guess
journalism that makes big leaps. They'll say something is related.
Right. I didn't know about the technicality of the word considerable. Is that, I mean,
I would say that means strong.
That means strong. Considerable means strong. Okay.
Yeah.
That's helpful.
Okay.
David, your brain sounds a little bit like mine. If it's anything like that, then you and I have both been equally frustrated with assignments since the start of this entire program. No offense to the program, just that kind of thing. Like, wait a minute, what does that mean, considerable? Like, that's a very subjective term.
Yeah, but this is the type of thing we need feedback on. So, yeah. All right, I'm going to stop the recording here because I want to tell you guys about some of the stuff. I'm going to try to stop the recording. I was going to stop. My Zoom has disappeared. There it is. Okay. There we go. Okay.